Okay, this is our second unit. CVPM, which stands for Constant Velocity Particle Model. So things aren't speeding up, they're maintaining constant velocity. The first example is a squirrel running along a fence. Here's my fence. And I've got the squirrel. And he's running that way. So he starts on the middle of the fence, so I guess I should draw a few more like this. Oh, got some on the table. Running that way. And we want to try and model the squirrel's motion. And then we're going to ask ourselves some questions. We'll first use some language like position, distance, and displacement. Then we'll move on to graphing, and then we'll move on to some problem solving. So let's do this together. If you can do all the stuff that we do in this video, you should be in great shape for the final. So we're going to define, as the problem says, the middle where the squirrel starts to be x equals 0. Then the squirrel moves forward 6 meters. Then the squirrel turns around, goes in the opposite direction from this point, 18 meters. And finally back in the forward direction for 4 meters. So the squirrel starts here, x equals 0, but ends up over here. The first thing we want to know is the position of the squirrel. That's going to be right here, and let's call this some positive and negative. So we'll call this direction forward positive, that direction negative. If the squirrel starts going 6 meters in this direction and then back over here, when the squirrel has gone 18 meters, where's the squirrel out at? Well, it must be 18 minus 6. You've got 6 here. All that's left on this side is 18 minus 6, which is 12 meters. So at this point, this is 12 meters, but it's negative because this is in the negative direction. And then the squirrel goes 4 meters in that direction. So when the squirrel ends its run, this is x equals negative 8 meters. See if you can make sense of that. The position is negative 8 meters. The distance traveled is all of the runs added up together. So 6 plus 18 and plus 4 is 28 meters. And then finally, displacement is the starting position minus the initial, or the final position minus the initial position. So if you start at 0 and you end at negative 8, we're going to take the final position, negative 8 meters, and subtract the initial position, 0 meters, which this just cancels out, and we still get negative 8 meters for our displacement. So that's the language that we used. Then we observe a different squirrel, and we see this squirrel is running, and we take some data as diligent scientists, and we take some distance time data. And we're curious about how fast the squirrel is moving. Okay. So here's our distance, here's our time. It would be good of us to first plot this. So I'm going to make a plot. It's going to be a rough sketch. Time's on my x-axis. Distance is on my y-axis. This is in seconds. This is in meters. What's the time that I go up by? 2 seconds. So 0, 2, 4, 6, 8. What's the distance I go up by? I go up by 5 until I get to 20. So here I go. 5, 10, 15, 20, 25. Yeah.
They want to open the door on you
Oh.
while you were
Oh, no worries.
what you were doing.
Yeah. We're just in the middle of the video. Alright. So we're plotting this data, just going through each data point here and putting it down on the graph, starting with 0, 0, then going to 2 seconds. At 2 seconds, the squirrel's at 5 meters. At 4 seconds, it's at 10 meters. And you should be pretty comfortable plotting at this point and drawing a line of best fit. Okay. I'm just circling my data points. So when we have this distance time graph and we're looking for velocity, we're going to look at the slope of the distance time graph. Well, how do we find slope? We should have got it from the previous video. Slope is rise over run. We can pick any 2 data points because this is relatively constant, and the slope is relatively constant. So let's go ahead and pick the easiest one, 0, 0, and the very next data point. So here's the one I'm picking, and I'm picking the very next one. So I first figure out my rise. I go from 0 to 5, so my rise is 5. My run, I go from 0 to 2, so my run is 2. I can start to put this into my slope equation. Rise is 5, run is 2, that is 2.5, and the units are what I started with here. This is 5 meters, 2 is in seconds, so I can add that to my equation and I get 2.5 meters per second. That checks out. When we measure velocity, we know that we've been measuring that in meters per second. So the squirrel is moving 2.5 meters per second. Okay, let's say that we have a velocity. Let's change context to, we're going to go to a biker who's moving at 6 meters per second. And I want to know how far they're going to travel in 60 minutes. Well, there's a discrepancy here. 'Cause one is measured in seconds, the other is in minutes, so we need to make these units consistent. Let's take everything to seconds. So my velocity is 6 meters per second. 60 minutes, that's a time. But instead of expressing it in minutes, I'm going to express it in seconds. So 60 times 60, I get 3,600 seconds. Okay. So I could think about this in terms of my graph, or I could think about this in terms of the mathematical model that we developed in class, which is velocity is distance over time. How far will they travel? Well, I'm looking for a distance. Distance is question mark, and now you're just plugging stuff in. You have your velocity, 6. You don't know your distance, so call that a variable. There's d. Divided by, you do know your time. What's that? 3,600, because I'm converting this into seconds. Okay. To get d by itself, I need to multiply by what's on the denominator. So both sides are multiplied by 3,600, which makes this term cancel out, which means that the distance traveled is just 3,600 times 6, and all of that will be in meters because that's a distance. This is our mathematical model. This is what's important, especially important for the CVPM unit. Know that. Okay. I'm going to pause it here and then start on graphs in the next video.